In this video, we're going to analyse the dolphin contact network using UCINET, then bring one of our metrics into NETDRAW as an attribute for the nodes and use this to display the network. So heading to our actual dataset, which was an edge list format, to actually get an idea of the number of nodes and edges in the network, we've already built a list of the number of dolphins on the Dolphins tab. And if you highlight these using Control-Shift-Down, and then look down the bottom, it tells you that there are 62 dolphins in the count. And looking at the edge list, you can actually do the same, highlight the number of edges by using Control-Shift-Down, and looking at the count, there's 159 edges in the network. And this is a valued network, so some of the net edges, like this one between Feather and Gallatin, has 6 contacts. So if you do the same, Control-Shift-Down over that number list and look at the bottom here, you'll have, as well as the count of 159, if you actually sum those numbers, you get 184 contacts, because some of the dolphins have more than one contact. Now, if you were presented with just edge list data like this, say from a movements register, like the NLAS, then you could actually build your unique list of property IDs or unique node list quite quickly by highlighting that data, copying it with Control-C, heading to a new tab and pasting it. Then I would just take all of the 2 names, use Control-C again, and paste these in below the other ones. Then if you head to the bottom of that list and highlight all of the names in the column, on the data menu, select Remove Duplicates, tell it to continue with this current selection and remove duplicates and OK, and it tells you that it had 256 duplicate values and 62 unique values remain. If you now head down, you'll see that there are only 62 unique dolphin names in that list, or unique node names. If you get rid of the 2 at this stage and rename that, you can then also sort this data and see very quickly that you've just got 62 unique dolphins in your list. Heading to UCINET, we're going to dichotomize our symmetrical network. So the edges like that one between Feather and Gallatin, we're going to turn that into a 1. To do this, head to the Transform menu, Dichotomize, select as your input dataset Dolphin Symmetrical, and name your output dataset as Dolphins Binary. The default settings for the dichotomization rule just turn anything greater than a 1 into a 1. So select OK. Then if you inspect that dataset, you'll see the node between Feather and Gallatin has turned into a 1 from a 6. And this network's symmetrical. So you can see the edge from Gallatin back to Feather is also a 1. We're going to use this for our analyses to keep things simple. Whilst we're working, it always is nice to visualize the network. So I'll just open up the binary network, and you can see this network's symmetrical in that all of the edges have arrows pointing in both directions. Returning to UCINET, we can calculate the geodesic distance. So this is the distance between all nodes using network, cohesion, geodesic distance. Input your binary dolphins dataset and let it automatically name this, and press OK. Now, interpreting this output, you can see that there are 62 rows and columns, and this is telling us that the shortest distance between B-scratch and beak is 3 steps through the network, or 3 degrees of separation, whereas the shortest distance between Feather and Gallatin is just 1 step, because they have a direct link between them. This table up here, there are 62 nodes in the network. So if you multiply 62 by 61, you get 3,782 possible pairwise combinations in the table below. And this tells you that of all of those, 8% of the pairwise combinations of two nodes are just one step apart, whereas 23% or 896 of them are two links apart in the network, and another 26% of them are 3 steps apart. So these are literally your degrees of separation. So it's nice to think of that in terms of the network. If we're moving between Feather and Gallatin, there's just one step. But if we're moving between SN100 to Web and then on to TR82, we find we've got 3 steps. Returning to the working directory, you'll find that UCINET has saved 2 files with the output data in it. You can open these with the D for display and select the binary geodesic distances dataset, and that brings up the adjacency table of that. If I were to do further analyses on these, I would just copy that and paste it straight into Excel in a new sheet, and then use the text to columns feature, and next and push finish to turn that into something usable. And from that you could find and replace all the zeros in the selection with nothing, and then plot the histogram, work out the frequency distribution, and look at the mean and standard deviation of the path length. Next, returning to UCINET, if we want to look at some other network metrics of cohesion, if we look up the density of the network, select the old density procedure because it gives some better output, and Dolphin's binary, and press OK. And this gives you a measure of 8.4%, which you can quickly look up under cohesion what this actually means, and it tells you it's the total number of ties divided by the total number of possible ties. For our network we have over 3,700 possible ties, and we had 159 edges, and because we've symmetricized the network we have 318 edges. Another interesting metric is the clustering coefficient. Now this coefficient, which ranges from between 0 and 1, tells us how clumped together the network is. In terms of, there are some areas where the network is highly clustered and other areas where obviously not all of the possible links exist. One way of considering this metric is that for a given node, if we looked at all of its neighbours, what percentage of links are there between all of its neighbours of what are possible? So in our network, if we look at Jet, it's got quite a few edges around it. How many triangles are there amongst its pairs of neighbours? So between number 1 and MUS you can see a closed triangle, but between MUS, MN23 and Jet there is no closed triangle, so the clustering is not complete. And this would match up to a situation like this, where of all of the possible pairings between neighbours of Jet, only one of them is realised, giving us a clustering coefficient for this example node in blue of 1/3. If we return to the UCINET output, we can head down and find Jet, and find that of all of its 36 possible pairs of neighbours, Jet has an individual clustering coefficient of 22%, whereas some of the others have higher and lower ones. Ones like Quasi don't have pairs of neighbours, so a clustering coefficient can't be calculated for those nodes. Clustering is one of the many different network metrics that can be interpreted in the sense of how quickly disease can spread through the network, and then if it's in certain areas of the network, how quickly it was spread around them versus onto others. And if it's in one part of the network, how quickly it can spread across to others and then infect all the nodes in that region of the network. Another common way to describe a network is in terms of how evenly certain characteristics such as degree or betweenness are distributed across the network. So here we can see that degree is not evenly distributed. There are some nodes like Jet that have got quite a high degree, and then other nodes like TR82 that have just got a degree of 1. So heading to UCINET, if we look up network centrality and power degree and select our binary symmetrical network, tell it that it's under-directed, or it may automatically detect it, and push OK. Then this gives us the degree of each node. So Beak has a degree of 6, whereas Jet has a degree of 9.
If we head down the bottom, we'll see that the degree centralization is around 11-12%. Now, if this were 100% or 1, then the network would be highly centralized, and some nodes would have an extremely high degree, others would have a very small degree. Next thing to do is
look at that distribution by copying it to Excel, open a new sheet and paste it in, and again use the text to columns feature. Tell it that the columns are a fixed width apart, press next. It automatically actually detects where to put the columns. So if that works correctly, you can just say finish. And now you've got data that you can use quite quickly to draw up a histogram. So first, we'll just do some descriptive statistics on degree by selecting, using Control-Shift down, all of the data. Tell it to put that output up here in F1 and to give us the summary statistics. And you can see the minimum and maximum is between 1 and 12. So if we head over here to make some bins between 1 and then just drag that down to 12, then if you head into data, histogram, select the degree values and your bin range, and make sure that you push show up the output, and we'll tell it to put the output histogram just here in L1 and push OK. And so then we have a frequency distribution of degree, and if we head down to our histogram, you can see that this is slightly positively skewed. Returning to UCINET, we'll now calculate who's in the core and who's in the periphery of the network and bring these data into NETDRAW to visualize them. So if you select network, core periphery, and categorical, and select your data set, and use the default values. This brings up a nice matrix showing a highly connected core of the network and then what's considered the periphery. And this also tells you who's in the core versus who's in the periphery. And rather than using these values to try and bring that in as an attribute into the network, UCINET's kind enough to give you a file, core partition, which if we open that using the display button and then selecting core partition, you can see that it's listed the dolphins in the core with an attribute of 1 versus those in the periphery with an attribute of 2. So let's save this data into Excel, where it's a little bit easier to format. Paste that into a new sheet. And again, move from text to columns. You'll see this is ordered alphabetically, which is the same as the node ordering in NETDRAW. So one way to bring this into NETDRAW as attributes is to highlight all of that and copy it. Then head into UCINET press data, data editor, matrix editor, and Control V just to paste it in. Then file and save this data set. Name it as dolphins binary core periphery, and you can close that one down. Then in NETDRAW, if you select this Open Attribute Dataset button, and then that tells it that what you're opening is an attribute rather than a network, and press OK. Now, if we look at the Nodes tab, you'll see that there is another attribute to each of the nodes. If these were ordered in the same order of the nodes, alphabetically, then they'll match up. So if we want to set the properties of the nodes and colour them based on our core attribute, and we may make the core ones red and the other ones blue, and then you'll see that all of those nodes in what's considered as the core of the network have now been coloured based on that attribute, whereas the rest are all blue. So what you can do is go ahead yourselves and analyse a lot of different node metrics in UCINET, and then bring these in alphabetically ordered as attributes, and then display the network using whatever metrics you're interested in.